Power sequencing has become critical, whether you're using general-purpose processors, FPGAs, GPUs, or simply microcontrollers. In this video, we're going to look at power sequencing measurements taken on a ZedBoard Zynq FPGA. We're going to look at the voltage rails, identify test points, and then make those connections using our logic analyzer. Then we can analyze that data in the Logic 2 software, dropping timing markers and doing further analysis. Let's get started with a step-by-step introduction. So what is sequencing? Sequencing is the ramp-up time or startup of the various power rails in your system. Your design must be verified both in the beginning, so while during the design process, but then also continually, every time there's a change to firmware, or maybe you add new peripherals to your system. So this implies regression testing. Our Saleae, we're finding that our Logic Pro 16 logic analyzer, which has 16 analog inputs, is increasingly used for power sequencing measurements as well. So users will hook up all of the digital lines, which also are analog lines, so taking 12-bit analog measurements of those lines, and then capture that data in our Logic 2 software. That can be done both at the bench or in the lab, or as regression testing that is done automatically using Python scripting. For demo purposes, I chose the ZedBoard, an FPGA board from Zynq. Now first I found the user manual, I looked at the sequences of all of the power rails, identified where they would be, which chips were actually providing them, and then went to the schematic. I was looking for identifiable locations on the circuit board, in this case it was shunt capacitors, in order to locate where these power rails were and find a place very close to the FPGA where I could measure them, because I wanted my signal to represent what the actual processor or the FPGA was seeing. So I went and marked them all and identified them, and then took that capacitor mapping and mapped it to the board. Now I took this photo with my phone and printed it out inverted so that I had, instead of white text on the PCB and a dark board, I had a white board and dark text. And this allowed me to go in and mark. Now I did use an ohm meter to figure out which side of the capacitors were signal and which side of them were actually ground, and I did that while the board was powered down. After labeling it, I soldered attach points. Now you could use a probe positioner and not have to go through soldering wire or magnet wire onto each of the capacitors, but I chose the magnet wire approach, and then I attached the clip leads from my logic analyzer to each one of those wires so that I could identify or measure the voltage at each one of those points. Now the wires are both color-coded and they have numbers printed on them related to channel, so I have two different ways of identifying which wire is connected to which terminal on the circuit board. This visual clue is carried into the software where the traces actually match the same colors as the wire themselves. So when I open up Logic 2, I turn on my analog channels, and then I press Run, and I start collecting data. Now in this case, I did go customize the names of each of my channels to match my the actual pinout names or the voltage rail names on the schematic. And once that data is collected, I flipped on the power. That gave me this nice square wave. It looks like everything turned on at the same time. But as we zoom in, we notice that there is some definite sequencing to these power rails. And on further investigation, it matches the data sheet. So we can place timing markers, we can annotate those timing markers, we can trim the data down so I have a smaller data set of what's visible using the timing markers as beginning and endpoints. I can save this data and then save it to a database or email it to someone else for analysis. But in all, this is just a quick jump into power sequencing using the Saleae Logic Analyzer. If you'd like to see more from us, please let me know.